So in the last video, we saw Kruschke's figure 9.1 that looks like this. And this video is going to focus on this figure, which is Kruschke 9.2, which uses grid approximation to understand this model. So whereas Kruschke uses coins and mints, I'm going to talk about students and teachers because it just helps me think about it. And so what we've got is a single student with some parameter theta that reflects their skill at answering questions. And that student has a teacher, a coach, preparing them for the standardized exam that has a parameter omega, which is a reflection of their effectiveness as a coach. And so we get a bunch of data. Let's assume it looks like this. And so this value y, these ones and zeros, implicitly indexed by row number, reflect whether or not the student got the question right or wrong. So if we could look at our flow chart, we've got this pattern of right and wrong answers that arise as random draws from a Bernoulli distribution with parameter theta, where theta reflects the skill of the student. But this is a hierarchical model, and the skill of the student is highly dependent upon the ability of the teacher. And the reason is that we're going to establish our prior. Our prior for theta is going to be a beta distribution. And it's going to be a beta distribution with two parameters. It's going to have a k value, which, to keep things simple, we're going to set as 100. And then we're going to have this omega value. This omega value, the effectiveness of the teacher. And so theta is going to be dependent upon omega. And what we're going to see with a very large k number is that theta is going to be highly dependent on omega. But what are our prior beliefs about omega? What are our prior beliefs about the effectiveness of the teacher? Well, in Kruschke's example, we don't really know much. And we set this as being a beta 2, 2. So we don't have much prior knowledge or strong prior beliefs about the effectiveness of our teacher. So with that review, let's move on to this idea of grid approximation. So here we're going to see grid approximation. Now, our goal, ultimately, is to estimate both the skill of the student and the effectiveness of the teacher, both theta and omega. So we're really interested in the posterior distribution of theta and omega given the data. So if this is the posterior that we're interested in, we're going to have to come up with a prior for theta and w. And that's prior for theta and w is shown here, and it's also shown here in contour form. So here are prior thoughts about theta. Here are the prior thoughts about omega. And what we have here is the joint probability of theta and w. So let's look at how we parameterize this. We said that back up here, we didn't know very much about the quality of the teacher. But by setting k equal to 100, what that implies is that the skill of the student is going to be highly dependent upon the quality of the teacher. And so here is all this shown in 3D. It's actually perhaps a little bit better or more easily seen in this panel here, which is essentially this thing shown here as a contour plot. So we don't have a really firm idea about how good our teacher is. And we can see that here. So here we've got on this axis theta. Here on this axis we've got omega. And look at the range of omega. It's all over the place. And here we've got omega and the marginal probability of omega. And you can see that this is, what's this? This is a beta 2,2. We don't have much idea, a very good idea of how good our teacher is. But we've got this huge K, which suggests that the skill of the student is highly dependent upon the effectiveness of the teacher. And you can see that, again, perhaps most easily in the contour plot. We don't really know what omega is, but look what happens if omega is 0.2. If omega is 0.2, then theta is going to lie within this very narrow range. And we can see that down here. So here we have the probability of theta given that omega is equal to 0.25. And you can see if omega is equal to 0.25, then theta, the skill of the student, is going to lie in this very narrow range. Similarly, let's say that the teacher had an effectiveness, an omega value of 0.75. Here we have the probability of theta given omega equals 0.75, and you can see fairly narrow range here, and you can see that same fairly narrow range here centered on 0.75. So now let's think a little bit, after we considered the conditional distribution of theta given omega, let's think about the marginal distribution of theta. So here's theta, and here's the marginal distribution of theta in our prior. And you can see that we really don't know, we really don't have a very strong prior belief about what the student's skill is. Why is that? Well, the reason is we know that the performance of the student is highly dependent on the ability of the teacher. But we have no idea how good the teacher is, and therefore we don't have a very strong idea about how much skill the student has. So that's the prior. Now let's move down here and think about the likelihood function. So the way that Kruschke approaches it is that he's going to say, okay, on the exam, the student got 75% correct. So instead of heads and tails, it's right or wrong answers. So what we're dealing with in terms of data are these data here and not these data here. So what we've got is, and maybe it's helpful to come here, is right now we're dealing with a likelihood function. There's our likelihood function, and there is our likelihood function right there. So we've probably got the probability of the data given theta and w. But recall a really important point from the last video is that essentially once theta has been established, we can ignore omega. And we see that both in the contour plot, both in the 3D plot as well as the contour plot. So in the 3D plot, there's omega, there's theta, and you can see that omega, these lines are parallel. So there is no effect of omega. All it really matters is theta. So here we have the probability of the data given theta and w, which is essentially just the probability of the data given theta, because we can ignore the w. We see the same sort of thing here on the contour plot. These lines are parallel. These lines are parallel because there is no effect of omega. And so these contour plots are sometimes a little bit tricky to read, but one thing you can think about is, okay, if you look at this portion here, where there's a very steep change in the likelihood with a change in theta, that's this bit here. The lines are really close together. Here, lines are further apart. And right up here at the top, the lines are even more widely spaced. So, that's our prior, that's our likelihood. And this whole game is grid approximation. And the beauty of grid approximation is you just take these values here, every value here, dot, 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 dot. Take every value here, dot, 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 dot. Multiply those two together, do the appropriate division to normalize this, and that gives us our posterior. So, what do we see in our posterior? Well, think about where we began. Had no clue how good the teacher was, but quite unrealistically, assumed that the performance of the student would be highly dependent upon the teacher. So now that the student does really well, or not so bad, 75%, so look at what effect that has had on our posterior beliefs for the teacher. So here was our prior belief of the teacher. Beta 2, had no idea. Student did really well. Student performance is highly dependent on teacher performance because of the high K, and therefore look at our posterior distribution of omega. It's really narrowed, and it's actually gotten quite high. And you can see that if we compare the contour plot. So over here, the omega goes over this range. Now the omega is going over a much smaller range. In terms of the conditional probabilities, what we can see is we've still got a very high value of K. And so our posterior beliefs about the student's ability are still fairly precise. So again, if we think about, if the teacher was 0.75, then the probability posterior distribution of theta, given that omega is equal to 0.75, this range here, that's this plot here, and you can see where it is. On the other hand, if the teacher was really poor, 0.25, 0.25, you've actually got to kind of extend these contours to see it, but this shows the probability of theta given that omega equals 0.25. So, in terms of the marginal probability of the student, the marginal probability of the student initially in our prior was here. We didn't know very much about the student because we didn't know much about the teacher. But now, student did real good. Therefore, we assume that the teacher did real good. And therefore, we assume that, after all, our student was pretty good. And so you can see that here with the marginal probability of theta for the student. It's gone from something fairly vague here in our prior to something more precise in our posterior. So I think there's kind of a take-home message here, and that is that you can see that we get a fairly rich analysis when we're dealing with an extremely simple example of students and teachers, and hopefully we can see the wide applicability of Bayesian data analysis, Bayesian hierarchical models, when you're thinking about environmental studies, where instead of students and teachers, you could have things like populations, parameters, and environmental parameters. And that's why these Bayesian hierarchical models are so important in the environmental sciences.